Hello. Good afternoon and welcome back. Our next session is going to be RISC-V startups. Our speaker is Neel Gala. Neel is CTO of InCore Semiconductors. He's co-founded InCore Semiconductors. Before that, Neel was amongst the founders of Shakti Processor Program at IIT Madras. Neel also has been an active contributor to the open source hardware community. Over to you, Neel.
Yeah. So the theme of the day, RISC-V, that's something that's common and that binds all of us here. And some of the most important features of RISC-V that we all agree on is its configurability, its modularity, its ability, it's being flexible, right? That's what gives us the free will to innovate, to mix and match, to add our own flavor to it. AI, ML, cryptos, whatever you want to be doing, you can do that with RISC-V, right? Right from IoT all the way to HPC, right? Now, taking the idea of modularity on the ISA, at InCore, we've stretched it further and we've said we also want configurability at the microarchitecture level, right? We don't want to be, so we want to mix both scalable at a microarchitecture level, right? So at InCore, we don't develop a single core. We in fact develop core generators, and not just one core generator, a family of different core generators, right? So today we have a two-stage core family, we have a five-stage Linux-capable core family, and so on, right? And the best part about core generators is you have a single code line, right? All your artifacts or your multiple instances, hundreds if not thousands, can be generated from a single code line. Your maintenance is easy, right? It's a designer's paradise. But obviously, it's a nightmare for verification, right? Because as soon as you're able to generate 100 or 200 different instances from the same code line, you have to start verifying all of them, right? And you cannot be using conventional techniques of conventional verification techniques to address this problem, right? You cannot be starting from scratch and designing or verifying every single instance that comes up. Your verification strategy has to be on a generation level, has to have the same scalability that your design has imbibed, right? So at that front, we've taken a step towards that, and we've realized that conventional techniques or conventional approaches to verify process is not going to work, especially if you're banking on core generators being the new norm, right? We have to look at verification generators, and there are two major aspects to it. One is the scalability of the test harness itself, right? Different cores, different instances, different features are going to require a different set of test bench. Are you able to scale and adapt to those? And secondly, the stimulus itself, right? How do you generate smartly, more easily and fast new stimulus for the new instances that you're creating, right? So we've mostly banged on Python as our vehicle to glory, right? And we've done a lot of open source. We've picked up open source tools. We've contributed back. InCore has also been the primary contributor and author of the RISC-V compatibility suite, or the compliance test, as you call it, right? All of which was based on Python, and all of which was made open source and donated by InCore today, right? So I'll be talking about some of those as part of today's talk. So three parts to Verif generators. The first one, as I said, was the test harness itself, right? You want to be able to build and adapt your test benches to the new features that come in. You've got interrupt controllers, you've got Plick, you've got Click, you've got Trace, all of that adding on. Your test bench should be able to adapt it and should be able to accommodate a new reference model and be able to compare state and do lockstep verifications and so on, right? Because different parts of verification for different needs will require different test harnesses, right? Either you're doing a log-based simulation where you want to be fast, or you're debugging a very complex scenario where you want to do a lockstep verification and so on, right? The next one is test generation. There are multiple layers. ISA being modular and configurable is good for us, but it's very bad for verification because it leaves everything on the table, right? Everything that the ISA does not specify is something that the verification guys are concerned. You have to know how your DUT reacts and whether it's still a legal behavior or not, right? And that behavior has to be defined by the DUT itself, right? ISA has no no mandates on those things. And finally, bringing everything under the same umbrella, we have a management framework which says if you want different test generators, if you want different test harnesses or test benches, I can make life simple by you giving me a simple API or a configuration file, and I'll go figure out what to do, right? So we have a management framework, which I'll talk about towards the end. So this is a classical verification flow, right? You should have seen this multiple times in Imperis or any other RISC-V DV or design verification talk. A typical slide or a typical flow happens, right? It's the most easiest one to set up. So you start off on the left as the assembly tests. These tests can be handwritten, they are generated, or they are populated by someone else. This is a compatibility test or your random programs from Torture, whatever it is, right? It's some assembly program that you have. Then you have the compiler. This is either GCC, LLVM, or your custom SDK that you've in-house built. You use that to compile the test, build a binary, right? The binary is then sent to your DUT, which executes the particular program and the test, and you populate it to the reference model also. Now, what's the reference model? The important feature of the reference model, or the only responsibility of the reference model, is to mimic your DUT, right? And this is mimicking parts of the ISA that are specified and parts of the ISA that are free for the implementation to choose, right? This cannot simply say, oh, I'm just going to do add and I can't figure out whether it's misaligned accesses or where my trap vector is or is it aligned. It has to be able to mimic your DUT as close as possible. That's what lies there, right? And today we have good amount of open source community driven simulators. We have Sail, which is the golden model from RISC-V International. We have Spike, which is a pseudo, community accepted golden model of sorts. We have Whisper, from Western Digital that has been coming up. So all of these can be used, but each of them have a limitation on what can be configured, what cannot be configured, how much closely they can mimic a particular DUT, right? So you'll have to play around. You will have to say, oh, this feature, maybe I'm going to depend on Whisper, or for this feature, I'm going to depend on Sail, or vice versa, right? And this is something I believe, it's time. This is a problem that every RISC-V chip vendor is facing. The solution is the same, but we all want to spend time and effort in, fixing it and building our own RISC-V configurable cores or simulators rather. But I truly believe this is one place and one effort that a lot of industries can come together, bless a particular configurable simulator so that verification can be made easy across the stack, right? Right from IoT to HPC, because you're only looking at architectural simulators. You're not talking about micro architectural simulators. You're not talking about internals of what you've implemented. You only want something that's configurable at the ISA level to start with, right? And that's what your reference model should be doing. We've also opened up a spec called the RISC-V config. This is a YAML specification that will truly be able to mimic my DUT, right? And that's where we should be going. So obviously the reference model should be blessed. We can't depend on our own validations. If you're going to use a reference model you've built to validate your own core, there's a chicken egg problem whether which one is right and wrong, and you'll have to go debug and you'll have to look at an external spec to figure out which one is right and wrong. But if it's community driven, if it's blessed by an external source, or if there's a consortium of 5 industries who have blessed it together, there's a higher chance that the reference model will never be wrong. Finally, there is the comparison part. So you've executed the test on the reference model, you've executed the test on the DUT, you are now somehow going to check whether they both gave you the same result, right? And this result could be in different ways. There are 2 ways that we will be discussing. One is the log based. After every execution, the DUT and the Spike dumps out a log of saying, this is what I've done, and does that match with the reference model or not? And the other one is a step and compare, where after every instruction, you sort of step, check, and you move on, right? So we'll look into both of them. So a similar diagram as before, but as you can see, the DUT and the reference model both now generate a log, right? This log file basically captures, after every instruction, what is the architectural state change, right? What has changed? Has the register changed? Has memory changed? Has CSRs changed? Did a flag get raised? Was a trap taken? Did privilege mode change? Any artifact caused by a single instruction is captured as a line in the log. If I have 500 instructions, or if I've executed 500 instructions, I'm expecting 500 lines in the log, right? The same log is what gets created by the reference model also. And it's simple. You have 2 log files. You simply got to compare them, do a diff. And if the diff provides no differences, the test has passed. If there is a difference, then you got to go debug and figure out what's wrong with the test, or what's wrong with the DUT, or maybe your reference model is wrong. You got to go get into that whole wheel. The good parts about the setup is it's very easy. It's very simple. It's been done multiple times by multiple people, and it's very straightforward. Very minimal scripts on day one. This is probably the best setup you can get in your early days of development of a RISC-V core, right? But the cons are larger tests will generate huge logs, gigabytes of logs, and doing a diff of the logs can become a problem. You will only know if there is a bug at the end of the test, right? So if you found a bug on the second instruction, you have to wait for the entire test to pass, generate the log, which may have millions of instructions, and then figure out, oh, the second instruction went wrong, right? So debugging is a little difficult with log-based comparisons. And more importantly, there are specific types of tests which you cannot capture here. For example, debug tests or interrupt tests, right? Delay sensitive tests. This test particular harness will not allow you to do that, because if your DUT has the ability to inject interrupts, you have to imbibe them in the reference model also, right? And that becomes difficult because the reference model is a single cycle simulator, whereas your DUT is, it's an out of order core or an in order core or whatever it is. It's difficult to synchronize them unless you have a test bench which can take care of that, right? So those types of tests are not easy to be done with log-based comparison. So to address those, we have a step and compare based mechanism. Now, here what happens is in my test bench, I have the binary of the assembly program. I've instantiated my DUT, I've instantiated my reference model, and I step them through every instruction, right? So I say run, step, compare the states. Are all the registers matching? If any change in the DUT, did you see the same change in the reference model also? And if that happens, repeat. Step to the next instruction, step to the next instruction. If it fails, you then have the ability to probe, poke, figure out what happened, dump the state, do whatever you want at that point, right? But you are at the point of failure, right? You have visibility of all the states, internal microarchitectural states as well, when it failed, right? So that gives you more insights when you're debugging for more complex issues. It's very good, but obviously it's slow because you got to run one instruction here, you got to run one instruction on the reference model, and then it's going to compare. And it depends on how much you want to compare. Do you want to compare only the register that changed? Do you want to compare all CSRs? Do you want to compare all memories? Do you want to do a checksum? Multiple things, multiple levels, which can give you trade-offs between visibility, confidence, and speed. Now, obvious thing is the synchronization. You want to make sure that your reference model, which is still cycle accurate, which is not a cycle accurate model, which is more of an architectural model, has to be synchronized at the same events or the same states as the DUT, right? So for example, if you see the DUT seeing an interrupt, you should somehow be able to synchronize it at the same point in program order for the reference model also, right? Now that becomes a challenge. Debug, for example, if the debugger wants to read something, you got to transfer the same packets from both sides, right? So a lot of interfaces or the UnCore part that happens in the DUT will now have to be synchronized to the reference model so that the reference model mimics the behavior as closely as possible and you're still able to compare states. So that's the step and compare model that we see. So in order to build the step and compare model, what we've done is using CocoaDB. CocoaDB is an open source Python test framework. It allows you to be simulator agnostic. It allows you to write test benches in Python, and it has its own VPI, DPI calls to downlayer simulators like Verilator, VCS or Exilium, whatever you want to call it, right? Whether it's commercial or open source, they support all of that, and you can move from one simulator to the other without affecting your test bench significantly, right? So we've been using CocoaDB, and your classical UVM like setup. You have monitors, you have scoreboards, you're comparing stuff. You can do all of that with CocoaDB today. And what we did was we instantiated our DUT there, which is the RISC-V core. And at the bottom, we had Spike. This was our reference model that we've used. Now, in order to use Spike in this environment, we had to modify things. We built Spike as a shared object file rather than a binary. We wrote an API around Spike, which allows us to probe spikes, halt Spike, read values out of it, read registers, read CSRs, read memory. So those entire API was built. And using Swig, this is a magic tool that I truly don't understand, but you are able to convert and use those C APIs in the Python world, right? So then in the Python world, I'm able to instantiate Spike. I have my RTL from the RV RISC-V core. I also have some uncore components. There's a debugger, there is an interrupt controller, there's a timer interrupt, all of that. And there's the sync routines in the middle, which will ensure that any event seen by the DUT is also seen by the reference model using the right API scheme, right? So obviously Spike had to undergo a lot of changes, a lot of churns in order to be compatible to some of these events that we want Spike to match, right? But we were able to get this going. Some parts of this setup is open source on our GitLab repositories. You can check it out with our open source core and Spike and see how it works. But the idea is when you're doing, really long tests or really complex cores, and you're not able to debug better, you want to go at the point of failure, step and compare works best. So the next equation of the whole verification generation is the test generation, right? Now I said ISA is configurable, which means there are already so many options here. I've gone ahead and added more problems by making my microarchitectural configurable. And now there are so many variables that the number of instances and corner cases are almost exponential, right? And in order to start test generation or to create stimulus, we need to split the problem down, right? And what we have done is we split it into three possible ways. The first is ISA. I want tests that make sure that I've interpreted and implemented the spec perfectly. If the spec says addition means 1 + 1 = 2, I should be doing that, right? That's all I need to check. I don't care whether there's overflow, there is carry, there is no, I don't worry about those, right? Whatever the spec has mandated, have I done that correctly or not? I need stimulus to just do that, right? And that's a good smoke suite. Believe me, at the end of that particular test suite, you have almost nil confidence. You only have confidence that you've understood the spec and you've written right Verilog or right RTL, right? It does not in any way tell you that you have a much higher confidence in your code. It's just that some software will probably run successfully on your code, but there are still bugs, right? Now, in order to go a little further, we go with the random program generators. That's the second vertical. The idea here is it's a mix of ISA and microarchitecture. We want to be able to quickly, randomly, get to the quick corner cases or easy to achieve corner cases very fast, right? And we believe generating enough random tests over time would allow us to achieve that. And now there are obviously more devious corner cases that you've not thought of and which could go wrong, which is where you need to go to microarchitectural tests, things like caches or branch predictors, which maybe your random program is not strong enough to generate those sequences. You got to handwrite them or you got to generate those tests specifically for your microarchitecture, right? So we've broken down the whole test generation problem at 3 layers. We've said we want to attack the ISA layer. We want to attack random tests so that I run these random tests on a nightly basis, right? And microarchitecture tests that whenever there's a change in my microarchitecture, I make sure I run all these tests plus 1 if I need to add a new feature there, right? And each of them takes a lot different set of times to build. ISAs are easy because you know the instructions, you know the specification, it's well known. Randoms are slightly more difficult because you got to figure out based on your microarchitecture and ISA, what are the pseudo-random constraints that you want to provide. And finally, microarchitecture is obviously the longest time to build those tests because you got to understand the microarchitecture, the design philosophy before you can actually attack it. So we've done some work in all of these verticals in the open source domain, and I'm going to talk about one of each that we've done. To start with the ISA compliance, 2 years back, InCore has donated its compliance suite. We built something internally. And today, if you go to RISC-V or RISC-V ARC test repositories of RISC-V, you will see the actual test suites that we've donated and generated, which are now available. And they're basically the gatekeepers for RISC-V branding today, right? If you want to use the RISC-V brand, you'll have to pass those test suites, right? Now, how did we create those test suites? Those are not handwritten. They were generated using a tool called CTG. It stands for Compatibility Test Generator. What we've done is this is more of a coverage-driven test generation mechanism. Internally, CTG uses a Python constraint solver. The constraints are provided not in SVUVM, but a much higher abstract Python evaluation functions. Right? These are more human readable. For example, RS1 equal to RS2 not equal to RD. That's my cover point. That's literally my cover point that I need to give. And the CTG is able to satisfy that and give you an assembly test, a minimal assembly test, to match or hit all your cover points, right? So while the test suites that you see on the ARC test are a subset, the CTG can take in much more complex cover points. The reason we restrict ourselves to compatibility is because compatibility is not design verification. As I said, just passing the compliance suite or the compatibility suite does not mean your design is bug free. But you can still use this to generate more verification tests rather than just compliance tests. Random tests. AAPG was an effort we started off at Shakti at IIT Madras back in 2013-14. And at InCore, we've been adopted this, and we've modified this and enhanced this internally as well. The idea is generating enough random programs gives you a high amount of confidence, right? And you can hit those corner case bugs very fast, at least the quick ones to achieve, right? And AAPG is the pseudo-random constraint generator, pseudo-random constraint program generator. You're given a mix of, I want 20% floating point, I want 30% memory, and so on. I can inject my own snippets of random codes, or my own snippets which I want to be sort of repeated at random points. You can do all of that with AAPG. And recently, there's also a feature which says you can generate self-checking tests, self-checking random tests. So if you want to take this to an FPGA and get a pass-fail from your GDB, you can sort of do that with AAPG as well. A couple of others are RISC-V Torture, CSmith, TestFloat. They all target different parts. CSmith, for example, is an assembler or a compiler tester, but it generates random C programs for compilers. We've sort of used it for verification as well. And finally, micro-ARC tests. There is no easy way out, but we've only raised the abstraction level. Remember, at InCore, we are doing configurable codes. We want that configurability to be exposed to the verification generators as well. Right? So we use Python to leverage the abstraction layers, to leverage configurability at that level. Right? I do not want to be writing configurable assembly programs, but I would rather write configurable Python plugins to generate the right assembly program. Right? So instead of trying to do configurability and parameterization at the assembly level, we do it at the Python level, which generates the underlying or the required assembly as flat. Right? So that's what UATG is. All of these tools are open source. All of these frameworks are open source. The links are also provided here. And finally, an umbrella framework. The idea here is I can have multiple test sources, as I said. I have CTG, I have AAPG, I have Torture, I have UATG doing all of that. Right? Now, if I was to maintain this, if I'm interested in all of them for my verification suite, it's going to be a maintenance nightmare. Right? How do I get all of these guys into the same environment? Is Ubuntu going to work? Is Python 3.8 going to work? Is something else not going to work? Are they compatible or not? So we sort of built a framework called the River Core. It's a dumb management framework, right? There's no intelligence to it. It just does three things. It talks to the test generators using an API, which is, can you generate, take this config, generate the tests, and give me a test list. That's it. That's the API, right? Your APG, Torture, compliance test suites can all be wrapped in your own plugins to provide this API back to the River Core. As simple as that. So whether you use Python, you use Java, you use Scala as part of your generation mechanisms, it's all hidden away, right? You just need to do that effort once, and River Core can keep calling your frameworks using different arguments based on your plugins. Once the test list is generated, the River Core will go to your DUT and say, okay, these are all the tests that you need to run. Generate the logs and keep it, right? That's your RISC-V target plugin, right? So the target plugin simply says configure yourself, build yourself, and simulate. Every simulation that you do generates a log file. I do the same thing with my reference model, where I can choose using River Core whether it's supposed to be Sail, it's supposed to be Whisper, it's supposed to be Spike. And it does the same. It builds itself, it configures itself, and it simulates. At the end, I finally have a report which says, did all the logs match? Did all the tests pass? If not, where do I go find the debug logs? Right? So in some sense, what we've done is we've split the entire problem of test verification and scalability issues into different parts. One is the test harness itself that we spoke about, and then the test generation. Right? So the plugin framework that you see here sort of absolves you from figuring out which test generator should I use and Is it going to have the same library issues or not? How do I invoke it? How do I get the output? Is it the same format? All of that is done by River Code today, right? It gives you a standard test list format, which your plugins or your DUTs and your reference models can consume very easily and start. This framework is also made open source today. So with that, I'm going to close and simply say that verification is a problem for all of us. I think this is a great opportunity for all of us to join hands, especially the industries. We are solving the same problem with the same solutions, right? I would appreciate if the solutions were different, but they're not, right? We're all trying to make it configurable. We're all trying to add features. We're all trying to be compatible with the next ISA extension that comes out. It's better to do it in public. It's better to do it with joint resources so we all can benefit from it. And probably that's where I'll leave today. Thank you.
Thank you. Thank you. Thank you, Neel. We have 5 minutes. We can take a few questions. Please raise your hand if you want to ask any question.
So do you do conventional ways of like writing unit level test benches and then monitor scoreboards and then use it at the top level? Is that the strategy? Or is it only like the top level that you mentioned where you do compliance and random?
So yeah, so the strategy that I mentioned is at the program level, right? So obviously, as your conventional digital design techniques, we do internal tests for each module and stuff, but they have different schemes. But typically, this is what our suite looks like when we are interfacing with the customer, the collaterals that we give, right? That's the typical suite generation mechanism that we would like to do. Yeah.
Hi, Neil. So you discussed about your generator, random generator. So is it different from the RISC-V generator, Google RISC-V?
Right. So the question is about RISC-V DV. Are we doing something different? I think RISC-V DV is just yet another test generator of sorts. It uses system verilogs and constraints and different mechanism of generating assembly programs or feeding into your pipe. You can add that here in River Core framework, right? You could simply have a plugin on the test generator side and say, I'm going to use RISC-V DV to generate tests for my DUT, right? So we've not used RISC-V DV ourselves. We've found our own test suites, APG compliance test suites, microarchitectural test sets, which sort of work. System Verilog is something not of, I don't think open source tools or Verilator even supports, and hence my aversion towards System Verilog based anything, right? But as soon as Verilator comes up to speed, I think it's just around the corner that system.
Question I have, like, what kind of RTL simulator do you support for this kind of framework?
Sorry, RTL
simulator, like.
So we use Verilator for most of our designs, but as I said, CocoDB allows you to switch from Verilator to VCS to any commercial tool by simply changing a makefile variable, right? You don't have to worry about the simulator itself.
Beyond time, we'll wrap the question answering now and move to the next talk. You can definitely catch up with Neel offline and ask all your questions. Thank you, Neel.